awards, including the NSF, oh, should I restart?
No, it's fine.
The NSF Career Award, the FOSR Young Investigator Award, George Valley Prize from APS, Sloan Fellowship, and many others. He has done some groundbreaking work in hydrodynamics of many body systems, holography, Lee Robinson bounds, and lots of other things. And he's in particular works at this exciting interface of condensed matter and quantum information, which is what he'll tell us about today. Please.
Okay. Thank you for the kind introduction and the invitation to be here. Oh, maybe I should click that off. Oh, hold on. It's going to be distracting. There we go. Okay. Yeah, so it's my pleasure to be here. Okay. Yeah, so today I'll be talking about work that I've done, much of it with my amazing PhD student, Chao Yin. At the very end of the talk, if I have time, I'll discuss some applications of the sort of main results today to condensed matter physics. And this is done with Carolyn Zhang, a postdoc at Harvard, and my new student, Ben, as well. Okay. Good. So this talk will be about sort of a synthesis of ideas between the theory of error correcting codes and sort of condensed matter physics. So let me begin by sort of telling you a baby version of this story in the context of the Ising model and the repetition code, sort of ideas from condensed matter and classical error correction. So maybe first at a high level, I'll sort of define an error correcting code as a system that protects logical bits by encoding them in a redundant way among some physical bits. And the sort of caveman version of an error correcting code would be called the repetition code, where you just say the message over and over and over again. And the more times you say the message, like the more likely the person is to hear it correctly, even if there's some noise and corruption of the message. So just a little bit of jargon here. So if we repeat our message n times, then we would say that we're encoding k equals 1 logical bit in n physical bits. And this code has a distance labeled little d, which is equal to n, because we have to sort of flip all the zeros to ones in order to change the logical message. If we see some combination of zeros and ones, then we know there was an error. All right. Now, if I think about, let's say, the all zeros and all ones, if I just kind of put a bra or maybe a ket around those zeros and ones, then those code words also happen to be the ground states of, let's say, the one-dimensional Ising model. So here I've written this as a kind of quantum mechanical Hamiltonian, where Z, of course, represents poly Z. In the sort of coding jargon, I would say that this product of Zi plus 1 refers to a parity check, because this is plus 1 if the two spins are in the same state, 0 or 1, and this is minus 1 if they're in opposite states. Okay. If we view this 1D Ising model as now a sort of quantum many-body system, it's a very nice Hamiltonian because it's a sum of commuting terms, meaning we can find the spectrum exactly. This Hamiltonian also happens to have a Z2 symmetry corresponding, generated by the product of poly X on all sites. And of course, this is the operator that would take this all zero state, one of my code words, into the all one state. And this Hamiltonian H naught has two degenerate ground states, the all zero and the all one state, which spontaneously break this D2 symmetry. And so from a sort of condensed matter point of view, we would say that this is a ferromagnetic phase of matter. And here by phase, we're really referring to the ground states. Of course, in 1D, the excited states are not magnetic. That's a sort of classic result from StatMech, but for this talk, we're interested primarily in the ground state physics. Okay. So the question we'll be interested in for this talk is, let's take this Hamiltonian H naught and add a small perturbation to it. And here, let's sort of focus on maybe local perturbations in space. So on our 1D line. And the question is, for any perturbation that we add, is the ferromagnet a stable phase? Or are there some perturbations that sort of immediately destroy this phase of matter? Now, I won't ask you any sort of clicker questions or anything, so I'll just tell you the answer. So this is not a stable phase. If you add a sort of longitudinal field perturbation, so single site poly Z's, you immediately destroy the ferromagnet. When epsilon is of order 1/n, the gap between the ground states and excited states will close, and so for sort of any order 1 epsilon, no matter how small, in the thermodynamic limit, we find a unique ground state, which is inconsistent with the ferromagnetic phase from before. And notice that this perturbation explicitly breaks the Z2 symmetry. And we can sort of understand that by noticing that this perturbation really picks out one of the two code words and says that, you know, this state has lower energy. Okay. So for this Ising model, symmetry breaking perturbation seem to ruin the phase. Okay. Now, what if we instead restricted ourselves to symmetric perturbations? For example, we could take on-site poly X terms. This would be the Ising model in a transverse field. And the Ising model in a transverse field is known to be stable, that the ferromagnetic phase is stable for this parameter epsilon sort of smaller than 1. Okay. So now we have a sort of whole radius of stability in this perturbation in which the ferromagnetic phase is stable in the sense that although the ground state may not be exactly degenerate on this finite chain, there are sort of exponentially small corrections to the ground state degeneracy and a finite gap separating the ground states from the excited states. Okay. So as we'll sort of discuss a bit more later, that these are sort of the properties that we're looking for to define a stable phase of matter. Okay, so it might seem at this point like the story is for this classical code, the repetition code, it protects a stable phase of matter against symmetric perturbations, but is sort of unstable against symmetry breaking perturbations. Unfortunately, that's not entirely right. So long-range symmetric perturbations can still destroy this phase. For example, if we added sort of epsilon over n times the sum over all zi's, zij's, if you choose signs cleverly on those zi's and zij's, you will destroy this phase of matter for a very small value, for arbitrarily small values of epsilon. Okay, so unfortunately, somehow like this classical code is not even robust against symmetric perturbations if they have sort of the right character. And so basically the question that will be motivating us for this talk is kind of under what circumstances are phases of matter, maybe very simple phases of matter defined by an error correcting code, can we really understand sort of when they're stable? And in particular, we might expect that there's some kind of relationship between the properties of the error correcting code and the stability of the phase sort of from a physics lens. Okay. And so the goal of this talk will be to present some answers to these questions. And along the way, we will be interested in answering these questions, not just for the ferromagnet, but for a broad family of other phases that you can define in sort of a more abstract kind of infinite dimensional setting. And to warm up to this, let me briefly introduce the idea of a classical low density parity check or LDPC code. I'll sort of try to present this in the most physics friendly possible jargon. I'm sure many people in the audience will know sort of the formalism underlying this, but okay. So we can think of generalizing our sort of repetition code, our 1D Ising model, by instead thinking about a Hamiltonian H naught. This will be our sort of fixed point in the code phase, which is a sum over what I'll call parity checks labeled by C. And each C will be the product of a sort of order 1 number of poly Z's, Zi. And this will be So it's a parity check code because of these products of z's either being sort of -1 or +1. And it's low density if there's a sort of order 1 number of z's in each term, and each zi shows up in order 1 number of times. So somehow this is a kind of q-body interacting Hamiltonian, although there may be no spatial locality. And indeed, in sort of the most interesting LDPC codes, they're defined on what are called expander graphs, so kind of infinite dimensional objects. Okay. If we choose an honest code where H0 has sort of multiple degenerate ground states, then this Hamiltonian would be frustration-free. And what I won't sort of justify to it all, but I'll just state as a fact, is that it's actually fairly simple to build a family of random codes for which almost surely in the thermodynamic large n limit, the number of logical bits stored is proportional to n, but also the code distance is also proportional to n, okay? Meaning that like the repetition code, we would have to flip a finite fraction of all the bits just to induce a single error in the system, but we would also, unlike the repetition code, sort of only need a finite overhead per logical qubit that we wanted to store, because this ratio k/n, often called the code rate, is sort of larger than 0, even as we take the limit n to infinity. Okay. And these codes are usually called asymptotically good codes. Now this Hamiltonian, if we have such a code, for each code word of this classical code, the product of Pauli x's will generate a Z2 symmetry. Okay. And so if we have one of these asymptotically good codes, this Hamiltonian has a very large symmetry group generated by these products of x's in every code word. Okay. Now, one thing you might notice about these phases that's kind of intriguing is that H0, if you think about the thermodynamics of this model, it would have a constant entropy density. Okay. So here S represents sort of entropy per particle, per bit in the system. And if I take the sort of 0 temperature limit of this entropy, I'm just counting the number of ground states divided by n. And so I get entropy k/n log 2. Okay. And I would say that this sort of seems to violate a third law of thermodynamics in the strongest possible sense. Okay. We have a sort of really extensive entropy at arbitrarily low temperatures. Of course, that conclusion is sort of unstable to the same kinds of perturbations that we saw destabilize the Ising phase. So I can again just like pick out a specific code word, in this case, the all 0 code word, as the sort of genuine ground state via this perturbation, and this will immediately restore a 0 entropy density. So in classical statistical mechanics, essentially because of this mechanism, there's always a perturbation to a Hamiltonian that only depends on Pauli z's that sort of restores the third law of thermodynamics. Okay. And so one of the sort of questions we'll be asking as we go through the talk is whether these codes can truly violate the third law for all perturbations. And we'll see that this is indeed the case when we look at quantum codes. Okay. Okay, at this point, are there any questions before I sort of move into the into quantum codes?
So when you think about thermodynamics, I guess at this point you can make that it's talking about local models. It's not really talking about these infinite dimensional systems.
Well, I think this conclusion sort of, so here, right, I'm not restricting to sort of finite spatial dimension. And I think this statement is sort of also not even concerned about the like few body interactions in H0. I can always sort of pick out one ground state as preferred.
Right, but later you'll find quantum examples nominally violated.
Yeah, we'll see that this conclusion is not safe in quantum mechanics.
Is it just a red herring because the thermodynamics is for local models?
No, well, okay. I mean, it's a question of taste. If you think that few body interactions, but but not in finite dimensional space is unphysical, then you don't care. But yeah, I mean, we'll have sort of few body interactions, albeit on one of these expander graphs, for which there's a sort of very strong violation of the third law. But yeah. Jay.
So, so is the notion of entropy here crucial, or are you just saying there's a macroscopic drastic? Or is that notion like, is there a difference?
I mean, you know, I'm calculating, so yeah, in some sense, this S of t will always be my proxy for, if not an exact, it's like the approximate ground state degeneracy. So the point will be that, like in the ferromagnetic phase, you know, K would be 1, but you would still have this log 2 factor, whereas in a paramagnetic phase, you would just have 0. That's sort of the point.
I guess in the dimensions, there's no distinction between like boundary, area, and volume law, right? So in what sense is constant entropy density that surprising?
No, well, because this is the entropy density of the Gibbs ensemble. So like you take the limit of the, you know, beta to infinity of the Gibbs ensemble. So this is not like entanglement entropy. I would agree maybe that entanglement entropy being volume law on an expander graph is not interesting necessarily.
In general, there's.
Okay, I mean, I think you know, there's a very precise sense in which we're making this statement, and whether or not you think it's interesting is a sort of
Well, no,
matter of
very
taste.
interesting. I'm just saying that, like, talking about the third law of thermodynamics, misleading
Why?
for the reasons I mentioned. But we
I
can
mean,
disagree.
I don't know. I mean, maybe people 150 years ago didn't think about expander graphs, but I think it's, I mean, I don't know. I think this is still sort of a statement that I'm sure I can like dig up in lots of textbooks. I just couldn't find something on Google Images after about 5 minutes that I wanted to cut and paste. But anyhow, anyway, I'll keep going. Maybe we can argue later if you want. Okay, so okay, good. So now let's talk about quantum LDPC codes. So the structure of a quantum LDPC code is kind of superficially very similar to the classical case. So we'll again have a sum of commuting checks, and the LDPC condition will require that each sort of xi and zi can show up only an order 1 number of times, and each check contains an order 1 number of polys. We'll also demand that all of the x and z type checks commute. We didn't really have to worry about that for the classical code, but we do for the quantum code. And when we satisfy these conditions, this is called a CSS code. And again, if we sort of choose the x and the z sort of properly, we may find that there are products of poly-z's that cannot be written as products of these checks, but which nevertheless commute with every term in the Hamiltonian. These will be called logical z operators, and ditto for logical x operators. These logical x and z will sort of form anti-commuting pairs. And if we have k of these pairs, we say we have k logical operators. Or k logical qubits, whatever. Okay. Like the 1D Ising model was our kind of like physics-inspired workhorse for classical codes. There's a sort of quantum analog of the 1D Ising model called the 2D surface code, which will be our workhorse for quantum codes. So here's a sort of illustration of the 2D surface code. So I have qubits living on every vertex, and everywhere you see an orange square, one of the checks will be a product of x around the sort of, or any orange region rather, including boundary triangles. I'll have a parity check, which is the product of x on the corners of that domain. And everywhere where I have blue, I have products of z's on the boundary of that domain. And you can see that there exists certainly at least one logical operator where the poly z logical sort of is a product of z's along a vertical line, and the x is a product on the horizontal line in this notation. You can sort of see that, for example, the red line always intersects an even number of times with the blue squares. In the quantum case, you can think of these as really one-form symmetries, because if I take this ZL and I multiply it, for example, by this, this parity check in the middle, the sort of blue line will begin to distort, okay? So this looks like a one-form symmetry. You can sort of use a language of one-form symmetries to talk about all of the quantum codes I'll be describing here, but I won't do that. Okay. And again, we're going to ask the same question that we did for classical codes. If we take the Hamiltonian H naught, which is now a sum of the X and Z type checks in this Hamiltonian, and I add an arbitrary perturbation V, am I in the same phase of matter, you know, up to some order 1 strength epsilon? Now, in the classical case, we said no, this would never be the case for general perturbations. But in the quantum case, we should be more optimistic, because in the quantum case, if we look at an operator P with any sort of few body operator, it always has 0 expectation value in the ground state unless it's one of the stabilizers, the parity checks that shows up in the Hamiltonian already. Okay. Or P could be a logical operator, but remember that these logicals in the surface code will be sort of extensive objects. So we won't see them in our sort of perturbing V. Okay. Now, why is this important? Well, if we think about doing perturbation theory in quantum mechanics, we're worried about finding a perturbation, right, that splits, that has off-diagonal matrix elements between the ground states of the surface code. And this argument tells us we would certainly never see that at first order in perturbation theory. But as we'll discuss a bit more later, there are sort of techniques to sort of push to higher and higher orders in perturbation theory. And this argument tells us that we still won't be able to split that ground state degeneracy until we can grow a logical operator. Okay. So intuitively, we already sort of minimize all of the parity checks or all of the stabilizers of the code. We don't really care, therefore, if we generate perturbations that just look like stabilizers. But we're worried about how long it takes for us to sort of build a perturbation that's a logical operator. That will take of order D, the code distance in perturbation theory. And for the surface code, D scales like square root n. So we have to go to sort of order square root n in perturbation theory, naively at least, to break the ground state degeneracy. So this suggests that that we indeed have a stable phase of matter. When we take the large n limit, the sort of energy splitting is falling off as this stretched exponential between our 2 degenerate ground states, e to the minus square root n. And this Hamiltonian H naught is gapped. And so the other sort of thing that we just need to ask is whether the gap will close under this process. Okay. And a little more precisely, we can say that maybe psi1 is like one of the ground states of H naught. Psi2 is one of the sort of ground states, loosely speaking, of H naught plus epsilon V. And we can say that these are in the same gapped phase if there's a sort of quasi-local Hamiltonian, which for finite time, under finite time evolution, sort of generates a unitary rotation between these two states. Okay. And we want, again, that sort of this, this rotation sort of never closes the gap of the original Hamiltonian. Okay. And maybe sort of a more kind of intuitive picture here is that we would like that there's some finite depth circuit, in quotes, that connects psi1 and psi2. For technical reasons, because we're talking about ground states of Hamiltonians, we'll really need to think about continuous time evolution. There can be some exponential tails that are captured by a finite depth circuit, but intuitively, this is the picture. Okay. And it was shown in a sort of very important paper about 15 years ago that this property, in fact, holds for the ground states of the surface code or toric code. I'll use those interchangeably in this talk. If you have a spatially local perturbation V of any. And so this is a sort of absolutely stable phase of matter. And this was, I think, our first example of such a phase in nature. Okay. Of course, we've never realized it yet, at least at scale, but in principle, this is an absolutely stable phase. Okay. Right. maybe just one sort of important remark, maybe in a broader sense that I should stress, is that these a phase transition between two different phases is not necessarily detectable thermodynamically. Okay. So anyway, if we teach sort of undergrads in StatMech that like a phase transition is detected by some non-analyticity in the free energy, this is wrong. This is a sort of more modern understanding of what it means to be in the same phase.
Sorry, I mean, quickly, so just,
Yeah.
From the more, local condensed matter point of view, I just wanted to, we have like these, let's say, fractional quantum Hall phase, right? Let's say some
Mhm.
topologically ordered phase, which we don't necessarily, can't necessarily exactly solve, but, I guess, I'm trying to get the sense of this absolutely stable in that sense, like, so is that an absolutely stable phase as well? That's in the last one third stage. Like in it, okay, maybe we can't prove it, but do we expect it? Or no?
Let me not comment on it because I haven't thought carefully about it. I mean, my answer would maybe be yes, but I'm like only slightly more confident than a coin flip in that. And there may be, and also, yeah, okay. I'll tell you mathematically precise things later in the talk, but I mean, yes. The fractional quantum Hall states are so far from the controlled structure that we have here that I don't know whether something goes wrong in that case. Yeah. Okay. So let me say, so at this point you might think that, okay, having a sort of quantum code with a distance that's growing somehow in the system size is a sort of necessary and sufficient condition to have an absolutely stable phase. This might seem like a reasonable guess, but it's wrong. Okay. So here's an example of a quantum code with a high distance. The Hamiltonian is, the code itself is really the surface code, but the Hamiltonian will be different. So here, maybe I'll take one of the parity checks, like let's say the one in the top left, I'll call that C1. I subtract that in H naught, and otherwise I take all sort of nearest neighbor pairs of checks, multiply them together, and that's sort of H naught. The Hamiltonian is just a sum over these sort of products of nearest neighbor checks, sort of seeded by a single on-site term. You can show that the ground states of this Hamiltonian are identical to those of the surface code. So again, we have a sort of high distance code protecting the ground state degeneracy, but it's not stable, okay? And we can do the same trick that we did in the Ising model. We can add a perturbation V that just is a sum over all the parity checks on site. When this epsilon is of order 1 over n, we will again sort of close the gap in the Hamiltonian and destroy the phase. So to understand what's going on here, if we just ignore this C1 term for a moment, we observe that this Hamiltonian H naught would have 4 degenerate ground states rather than 2. We would have the 2 degenerate ground states of the original toric code. And then we would also have 2 more ground states, which look like the toric code, but with like very special poly Y errors on, I don't know, some order 1 fraction of the sites. And these Y errors are chosen to flip every single parity check exactly once. Okay. So the product of all the checks is still, of all nearest neighbor checks is still +1, but each individual check is violated on its own. And so now adding this C1 and adding this perturbation V looks exactly like adding longitudinal fields to the Ising model. We're just picking whether we want the sort of honest logical sector or this fake logical sector to be the true ground states. Okay. So having a good maybe not asymptotically good quantum code, but having an okay quantum code is not enough. The distance sort of being square root n does not protect this phase. So if it does not, you might ask, what does make the toric code a stable phase? And this was something that was worked out back in 2010. It was called local topological order. So the property of the surface code that makes it a stable phase is intuitively the following. So if I take any sort of stabilizer of the code, let's say an X-type stabilizer will always look like potentially some product of multiple loops of poly X's. Yes.
So, in the language of necessary and sufficient, you just said that the code distance is growing with the system size is not sufficient. Are we saying it's necessary or it's not even necessary? And is this a necessary and sufficient condition or a sufficient condition?
I'm not sure if code distance growing with n is necessary, but we don't know how to prove it if you have a distance that doesn't grow with n.
Okay,
Um,
and, local topological order is necessary and sufficient.
Yes. Yeah, with code distance, which is at least log n. I'll show you that later, but yeah.
Sufficient.
It is
Uh,
sufficient, but not necessarily.
Well,
necessary.
I don't think we know it's necessary.
Sure, okay, yes, I would say sufficient. I mean, there are, yes, okay, in an example like this, obviously it doesn't have local topological order. Okay, yes, it's sufficient to, that's fair, yes. Okay, okay, so in the toric code example, we have stabilizers that look like products of a loop, products of x's around a loop. And we can always write this as the sum, as the product of checks that sort of are the local spaces, you know, in this lattice that fill the middle of the loop. Okay. And in particular, if we take any check in any one of these loops, we can always sort of write it as a relatively small number of these C's that show up in the Hamiltonian, not in this H naught, but in the bare toric code Hamiltonian. I'll later call that check soundness. But I think historically the way people thought about this was that there's no local operator O, which if you just sort of restrict to the Hamiltonian in this region, there's no local operator O that acts non-trivially in this region. So you have a kind of local version of a nil-Laflamme condition from error correction. Even one way to say it would be that with this Hamiltonian, if I just look at a region that's away from this check C1, it really looks like I have four logical sectors, or four logicals, the code space of logic of dimension 4. I have these two states, but I also have these two states. So locally, I kind of can't tell whether these states on the left or these states on the right are preferred. I need to have some global knowledge. And that's why we would say that doesn't have local topological order. Okay. All right. Of course, this condition only sort of holds if this set S bar is smaller than the code distance. Once we grow something that's of order the code distance, we could genuinely build a logical operator. So this condition will fail. Okay. So the last bit of sort of background material before I can state our contribution is to mention that just like we talked about classical LDPC codes that had sort of nice properties where code distance and the number of logical qubits scaled with n, people after a long effort finally found quantum LDPC codes that also have these properties. Okay, and the constructions are very complicated and I don't really understand them, so I won't. This will be basically all that I say about them, other than they can't be embedded in finite spatial dimensions. That's not so hard to see. But okay. All right. So the surface code, you know, is a quantum LDPC code. We usually don't say it like that because you know, there's some sociology there, but the surface code, you know, it's a sum of few body parity checks, and each bit is only involved in an order 1 number of checks. So it's an honest quantum LDPC code. It's got a distance which is square root n. So we might ask whether the absolute stability of the surface code could really be understood maybe in a more abstract way as following from some fundamental properties of an LDPC code, but maybe these properties could be understood for more general codes as well. And maybe we can ask a question of whether other families of LDPC codes also define stable phases in the same sense that the surface code is stable. Okay. And so, okay, with that sort of question, let me now sort of tell you the answer. Okay. So this is work my student Chow did last fall. So we'll consider the same setup that we did before. The Hamiltonian is H naught plus epsilon v. H naught is a sum of parity checks of a quantum LDPC code. And we can basically have any few body perturbation V. I'll define that maybe slightly more precisely a little bit later. And we show that as long as this code H naught exhibits check soundness, which I'll define on the next slide, then the ground state degeneracy of H is at least approximately robust, so long as the code distance is sort of at least log n. And by robust, what I mean is that there exists a sort of quasi-local unitary U that rotates the ground state sector of H naught, remember, which is 2 to the k degenerate. We have k logical bits, and it will rotate this into a sort of another sector separated by a gap from the rest of the spectrum in H naught plus V as well. And the energy splitting will be sort of exponentially suppressed in distance, and ignore the blue text here. Okay, yes, and this unitary U is sort of quasi-local. So this has all the same sort of bells and whistles that we wanted to say that, for example, the surface code was a stable phase under perturbations. It turns out that all quantum LDPC codes with check soundness will also inherit this property, as long as they're not constant distance. Well, okay.
Just about the results, so because you're saying that V greater or equal to log n, so this is also valid for hyperbolic codes?
We didn't check this check soundness condition for the hyperbolic surface code. But for hypergraph product codes and the good families of LDPC codes, they are very check sound, and this result holds for them.
Are you gonna remove the quotations or?
Eventually, I removed the quotations in a couple of slides. Yeah.
Great, thanks.
Okay. Yes. So let me also mention some sort of other related work. So Chow and I were sort of inspired by this work here from last May, which studied sort of sub-expander codes and their stability properties. And yes, so as I said, we were kind of very much inspired by that work, and we kind of used our technical methods to kind of improve on this and to get sort of all the way to the stability result for constant rate codes on expander graphs. And then there's a sort of contemporaneous result by de Rooij et al. That has somewhat different assumptions if we want to sort of nitpick and a sort of different regime of validity than our result, but maybe kind of morally they have the same result that we do. Okay. Right, so what is check soundness? So remember that the Hamiltonians that we're interested in will basically look like this. We can slightly generalize it and put some kind of prefactors in front of each check, but remember that the Hamiltonians will be a sum of parity checks like this. And these parity checks generate the stabilizer group for the quantum code. These generators may sort of be redundant. I might include some terms in this sum over CJs that are products of other CJs. That's okay. But I say that the code has check soundness if all stabilizers, all elements of the stabilizer group that act on some number m sites, which is basically smaller than the code distance. I want all of those stabilizers to be products of a relatively small number of the elements of H naught themselves, okay? And yeah, in particular, we'll demand that K, the sort of number of terms in this product scales at most sort of polynomially with M, the number of sites on which the stabilizer acts. And our proof requires, when I said check soundness, what I really mean is check soundness with A less than 2 for a general code, or any finite value of A if the code is embeddable in finite spatial dimensions. So basically the A less than 2 is just a requirement coming from the expansion property, the potential expansion properties of the Tanner graph of the code. All right. And all of the sort of popular LDPC codes, quantum codes with constant rate actually have linear check soundness. So they're well below actually linear check soundness is optimal. That may be easy to see. from the LDPC condition. So basically all hypergraph product codes, these like quantum Tanner codes, all of these constructions people like are check sound, and therefore our theorem will apply to them.
They're so complicated to understand them, but you're able to compute the check sounds.
Well, so I do understand hypergraph product codes, and that's the only one we had to check this ourselves. It turns out that for other codes, people had a sort of bizarre name for this, like small set co-boundary expansion or something. I mean, some fraction of those words is
Oh, they
correct.
checked it themselves.
Yeah, so this was like a quirky property of these codes that they just happened to know, and Yukon actually told us that they knew it, so that was convenient.
That's not so quirky, it's related to coding.
Sure, but anyway, I think sure. Anyway, so they knew that this property existed, but yes, I think our name is maybe a little bit more.
That's awesome.
Is it better? Yeah. So anyway, we've rebranded that property as check sound. And for those of you who know coding, this is a sort of natural name because it's very much inspired by sort of the usual notion of soundness that people are interested in. But it's kind of like the reverse in some sense. Okay. So just to sort of emphasize that check soundness isn't so strange, if we go back to the surface code, in my view, this is actually maybe a more elementary way of explaining the stability of the surface code. This is check sound because if I take any stabilizer, which remember is a product of x's or z's along a loop, a closed loop, then just by like high school geometry, the perimeter of this loop bounds the area enclosed within the loop by order perimeter squared. Okay. And that's precisely check soundness with a equals 2, which is sufficient for our theorem to apply. So therefore, our theorem sort of also includes the surface code. It's a 2-dimensional code, so it can have any algebraic check soundness and be stable. But our theorem actually does give you something new about the surface code stability, because we actually prove the stability of the surface code to all few body perturbations, including those which are completely non-local spatially. So that was not a known result, but as far as I know, at least, but this is now something we've established. Yes.
What is Q?
Q is anything order 1, but I didn't want to call it, so K local is more standard in computer science, and it just means,
But you already have a K.
but I already have a K, exactly. We have a finite dimensional alphabet, so yeah. Yeah. Okay, and now we can return to our second law of thermodynamics. Third law of thermodynamics, thank you. And we see that now this constant entropy density is absolutely stable, okay? So because we have this sort of extremely tiny energy splitting in the ground state subspace, when we take the thermodynamic limit, the entropy density is finite, not only at the sort of code fixed point Hamiltonian H0, but also for arbitrary perturbations away from that point. So in some sense, we have an entire phase of matter where the third law of thermodynamics, being that, entropy density should vanish, that statement is false, sort of in some neighborhood of the fixed point. Okay. All right. So these are kind of all the high level points that I wanted to make. Are there any questions at this point? Yes.
In ordinary thermodynamics, we have multiple equivalent formulations of the third law. For instance, that it is impossible to cool to 0 temperature in any finite number of steps. And again, in ordinary thermodynamics, according to my understanding, those formulations are equivalent. Does your theorem break all the formulations of the third law?
That's a good question. I don't know the answer, but that's very interesting. It would be very interesting to know the answer, but I don't. Yes.
Sorry, so, but the surface code is not your example, right?
No. The surface code is fine.
Exactly.
But you use these kind of constant rate quantum LDPC codes, like the hypergraph product codes. They are sort of robust phases of matter with constant entropy density. Yeah. All right, so, oh, yes,
I guess, so I've also heard this statement said for like classical spin classes. But maybe the point is those.
that would be fake news. Yeah. Well, I already told you how to sort of restore the third law of thermodynamics. For a spin glass, you just add a longitudinal field that picks out one low energy state.
Oh.
Yeah.
So do not.
So, yeah. No, but here, right, so in a nutshell, the reason you can't do that trick for quantum code is that by its very construction, there's no tiny logical operator. You can think of that trick for classical code is if you think of the classical code as a quantum code, it's like the Z logical operators are single site polys. So adding a longitudinal field perturbation is like saying this logical sector should be the true ground state. But you can't do that in a quantum code because the ground states are all highly entangled. So that's the magic. It's truly a quantum phenomenon. You cannot do this classically. Okay. You can with restrictions. I'll make some comments about that in a few minutes, but there's truly no requirement on V other than it's not an n-body interaction. Yeah.
If you start to allow your perturbation to like grow with system size or something, when does it break? Do you have a sense of like?
We didn't carefully look at this, but my rough guess would be that as long as V is sort of, as long as this Q scales as D to some power smaller than 1, my guess is that our stability result would still hold, but there may be like really nasty constant prefactors in our proof that would diverge with D in a dangerous way. That, like, I think you could go through our proof and check, but we didn't do that. Yeah, but it's an interesting question. Okay, let me, in the interest of time, maybe I'll spend like 5 minutes kind of sketching some of the mathematical methods that underlie the proof for anyone who's interested. It is rather technical. Here's the slide where I'll sort of tell you the specific assumptions with no quotes. So the Hamiltonian is a sum of all the stabilizers of the code. And this should be greater than or equal to, but this lambda means like we're not relying on H naught having an integer spectrum. So there are some results in the literature that are very sensitive to H naught having an integer spectrum, but this will not be one of them. Okay, we just need a gap, and in this construction we'll have a gap. Yeah.
This one doesn't play a role, this one.
I mean, it's just
to
that's
make
constant.
that zero.
Yeah. It's just having a constant gap. We demand that the code has check soundness. I've already defined that. And okay, that should be plus kappa S, but otherwise this formula tells us sort of what we mean by locality. So we just need the perturbation essentially to be exponentially suppressed when it acts on a large number of qubits at once. So any Q local perturbation will sort of have this property. Okay, maybe up to rescaling. So again, we don't require any kind of locality with respect to kind of the code checks themselves. So for the surface code, you can have completely spatially non-local perturbations, and our theorem is still appropriate. Yes.
Here's the sign on the kappa curve.
No, it should be plus.
Maybe taught us this. It's not that I'm very good. He told us this formula earlier today. Yesterday.
But I also said it like 60 seconds ago. There was a typo.
Oh,
So
you did? Oh,
yeah.
I was saying I was focusing on each zero.
I definitely
Oh,
did
sorry,
say
sorry.
that. Anyway, that's fine. Okay. So now with those assumptions, basically we're just going to explicitly construct the unitary that rotates us from the old to the new ground state subspace. So we start with this H naught plus epsilon V, and so the goal is basically to build a sort of a quasi-local U1 that undoes the perturbation at sort of first order. So if you think about this perturbation V, in general, it might sort of perturb a code state into a not code state, induce some error. We would like to sort of find a unitary that rotates that error away. So here, the sort of top left part is the code space, bottom right are the excited states. And our goal is basically to do some rotation that kind of makes the Hamiltonian block diagonal between the code states and the excited states. And then there will still be some perturbation that mixes them, but it will be at a lower order in perturbation theory. And again, we want this D2 and V2 to sort of still be local in this computer science Q-local sense. And the key idea is that we can do this because the Hamiltonian H naught is exactly solvable. Okay? So basically, if we look at the form of this perturbation V, we can just explicitly write down U should be generated by some kind of Hamiltonian A, and A looks kind of like V, but the more errors that, the larger the syndrome of the error that V causes, kind of the smaller rotation we need to apply. That's sort of technically very helpful. Okay. And okay, trust me that this works, and we can just do it many, many times. Okay. And we carry out this perturbative series up to an order D, where D is the code distance. At that point, we could potentially grow a logical operator, and we have to stop. Okay, we might genuinely split the ground state degeneracy in a way that we can't fix. Okay. Yes.
Do U's get closer and closer to identity?
Yes. Yeah. So each U, like U1 was of order epsilon, U2 is rotated by order epsilon squared, and so on. So this converges. Yeah. And the series converges even in this kappa norm sense. So it's truly local. Okay. And again, this sort of D star doesn't split the ground state degeneracy. It doesn't sort of shrink with perturbation theory, but it's still sort of degenerate between all of the code states. And okay, so for the sort of technical people, for the people interested in these details, it's really critical that we don't use Lieb-Robinson bounds in this proof. So that's the sort of ordinary way you think about locality in many body physics, mathematical physics at least. But it does not work here because these are expander graphs, and Lieb-Robinson bounds are just not strong enough to get a convergent series here. So we really use techniques that are more inspired by the cluster expansion from statistical physics to prove the convergence of this series. And this is essentially to get these kind of volume tail bounds that we want. Where does check soundness enter this proof? It basically enters in two places. So first, as sort of technical remark, check soundness is just useful to kind of control the convergence of the series, which is most dangerous by, at every order in perturbation theory, we have to rotate this D. And okay, check soundness just tells us that there aren't so many terms that we need to worry about. And the other thing check soundness does is it actually ensures that the gap doesn't close. So if you didn't have check soundness, the proof can break in one or both of these places, and indeed it can. Because we have examples where phases are not stable in the absence of check soundness. And for what it's worth, all of the examples that I showed would violate this second condition. Okay. So I told you about the stability of quantum codes, but you can also sort of use our results to learn some things about the stability of Hamiltonians in phases protected by classical codes. So if you have a classically check-sound Hamiltonian, then it is stable to all symmetric perturbations. That is maybe sort of not so surprising given the quantum result. Okay. Unfortunately, many interesting classical codes are not check-sound. For example, the repetition code is not check-sound because if I multiply a long string of like zi plus 1, I get zi plus k, which is still two-body, but it was a product of many checks. So it's not check-sound. But if you demand that the perturbation is spatially local, then our theorem also proves something which was already known, namely the stability of the Ising model to local perturbations that are symmetric. Okay. Okay. There is maybe one interesting new thing for the Ising model, which is that our construction of U has a much stronger tail bound than the known results. And for reasons I'll mention in the last couple minutes, this can be helpful. So ordinarily, one derives these quasi-adiabatic unitaries U using some and sort of controls their locality by Lieb-Robinson bounds. And as I'll discuss in a couple minutes, when you have Lie-Robinson bounds, the fraction of, let's say you can grow an operator potentially to be very large, and the sort of weight that this large operator will be suppressed by only drops off exponentially in the diameter of the set you act on. But here we'll have exponential in volume suppression, and as I'll now kind of quickly mention, that can be useful. So these tail bounds on U sort of suggest new ways to distinguish between phases of matter. If we take, let's say, an Ising ferromagnetic phase, we proved that if you have this exponential in volume tailed U, something called the disorder operator, which is the product of Pauli X's, namely the symmetry operator of the Ising phase. If you multiply by that operator in some region R, we prove that any state which is connected to the Ising fixed point by this unitary U will have an exponential in volume suppressed disorder operator. And this is maybe sort of intuitive from a kind of cluster expansion or Taylor series type argument. It's like you have to sort of somehow rotate every single Pauli X in this expression into something that looks like a Pauli Z to have a non-zero expectation value. And that's like you would need to pull down R terms from this U. So if the rotation is small, you would expect that you have to do that R times, which gets you this. And this is interesting because there are certain states that naively look ferromagnetic, but don't have this property. So there are states called Roxar-Kivelson states that can break Z2 symmetry spontaneously. But suggestively, they appear not to be in the same phase of matter because this disorder operator is actually only area loss suppressed, not volume loss suppressed. Okay. So we certainly know from this property that there is no volume-tailed exponential unitary U that rotates you from the Ising phase or from the Ising fixed point to the Roxar-Kivelson state. Okay, and conjectured on the assumption that volume-tailed U, or perhaps definition, if you like, that you should have a volume-tailed U to connect you between 2 points in the same phase. If that were true, then the RK state would be in a new phase of matter that we couldn't have identified with our old techniques. But I think this is sort of a conjectural direction, potential application for these ideas, but I think it's quite interesting. Okay, maybe let me just try to quickly flash. So another kind of application of these, or rather a sort of result that we needed to get that theorem are volume law tailed Lie-Robinson bounds. So these are kind of much better than the standard ones that I've used in the past. And what we basically want is the following. So you take an operator A of t, evolve it in time, and sort of collect all the terms that act on sets of size S. And our goal is to say that all the terms that sort of act on sets S, which have a large volume V, sort of all of that operator is exponentially suppressed in V when V is sort of large compared to what you might call the Lie-Robinson light cone. Okay. And okay, the tail bound is much better than you would have in a sort of ordinary method where you would just get V to the 1 over D. And let me just mention that this sort of allows us to prove theorems on the classical simulatability of quantum dynamics. So in particular, if you want to do simulations to some finite time t, but you want a sort of guarantee on the accuracy epsilon, this can be done in a sort of polynomial and epsilon, using polynomial and epsilon memory on your classical computer, which is a sort of major improvement over known results. And the point is basically that because we have these Lie-Robinson bounds, we can show that you can essentially just throw out, like if you grow Pauli strings that are too large, you just ignore them. And that step will not sort of degrade the accuracy of the computation because of this bound. So that's sort of the way that the algorithm. Okay, let me just sort of stop here. So we've seen that there's a relationship between robust, sort of certain robustness features of classical and quantum codes and the robustness of corresponding phases of matter. And this analogy holds for these LDPC codes in infinite dimensions, which define very interesting phases of matter with this non-zero entropy density that I talked about here. These also turn out to have glassy dynamics, quantum self-correction, et cetera. This is work I did with my former student Yifan, who's now here, last year as well. Yes, and I think that sort of some of the methods that we needed to prove these stability bounds on codes also will be very interesting in other sort of applications in mathematical physics. One of them I already sort of described to these volume law tailed Lee Robinson bounds, but I think there could be many other interesting applications of these methods in the future. So thank you. I'm pretty sure that, so if you're referring to this theorem, I'm pretty sure that it does work for time-dependent things. I just.
The absolutely stable phase, like when we say it's a front thing,
I guess, well, okay. So I feel like that's a sort of dynamical question. And I'm a little bit, yeah, I don't know how confident I would be. It might work, but there could be a lot of other complicating factors.
Especially to like forbid like resonance.
that, yeah, that's like, if I just add in perturbations, that's kind of turn on some like excitation and then break them.
Yeah, because you don't have energy conservation there, I'm sort of not so sure that you should expect stability, but maybe there are sort of cases where it's possible. I'm not sure.
You talked about like these like unitary perturbations, but what if you have like dissipated perturbations? Like how does the system like mixed state phases of matter and like the robustness within that?
I mean, I think the short answer is we don't entirely know. There are some recent results on like quantum bottleneck theorems that suggest that maybe even like the Gibbs states of some of these LDPC codes are sort of very robust. And this would be related to this story about like quantum memory in these codes, but we don't have a sort of statement like the finite temperature Gibbs state is stable. That's an open problem. Yeah.
Other like are there sort of bats that prepare the quantum LDPC code? I guess just thermal or what bath would you be preparing?
It's probably not, I think, that we know of now, and the reason is basically because we don't have quantum sort of usually we don't have sound asymptotically good quantum codes. I think people are claiming they'll have them soon, or maybe they already exist, but I don't think I've seen it yet. If we had that, then for sure it would be easy to prepare. You would just kind of locally try to measure stabilizers, and it would be basically like Gibbs sampling, and you would cool down in a sort of annealing fashion and cool into the codes, into code space with sort of small fluctuations at the top of it. The reason this will not work for many of the codes we know is that they have more of this like, they have a very complex energy landscape where there are a lot of these like sick minima that have very, very low energy, but are far from all code words. So that's, I think Vedika called this the like topological spin glass, but that's sort of why it would be probably very hard to prepare these efficiently, starting from some product state. The last question.
So do your results have any like implication for active quantum correction, feedback, measured stabilizers, or have you thought about that?
I mean, from this perspective, I've thought about it. What this paper basically pointed out was that you can do like these LDPC codes are sort of very good self-correcting codes. Maybe they don't necessarily have high thresholds, but the lifetime is very, very long information. And so these are sort of very useful for maybe like measurement free error correction with low depth circuits, etc. So maybe that's sort of a partial answer to the question.
Okay, let's thank Andy again.
Stop.
Am I allowed to stop it?
I made you the host.
You made me the host. Oh.